The purpose of this movie is to explore rolling motion. So what is rolling motion? Well, if you take a look at this simulation, you might be able to convince yourself that rolling motion is just a combination of two kinds of motion that we're already familiar with. First of all, there's rotation happening. And at the same time, there's also some translation happening. If you take those two motions and put them together, then you have rolling motion. And in the simulation you just saw, the rolling motion seems to be rolling without slipping. It doesn't have to be that way. Here's another example where the rotation is going in the opposite direction that it was previously. If you saw something like this, you would probably guess that it was slipping, and yet that's still rolling motion. All right, so let's break down this motion a little bit more and think again about the rotation and the translation separately and then put them together. So if I asked you, what are the points on the edge of an object doing when it's rotating, you might draw velocity vectors that look something like this. The points on the edge of the wheel are all moving with the same speed, but the velocity depends on where the point is located around the edge of the wheel. And if we know the angular velocity of the rotation, then we also know the linear speed of the points on the edge of the wheel. The linear speed will be omega r. So the length of each of those red vectors is omega r. You can do the same thing if you imagine an object that's undergoing purely translational motion with no rotation. What would the linear velocity look like for each of the points on the edge of the wheel? Well, if we take a few examples, they'll all have the same linear velocity, and that linear velocity will be exactly equal to the velocity of the center of mass. I've added a vector in the center of the object that has translation because that point would also be moving with a velocity equal to the center of mass. Actually, that is the center of mass. And actually, in the rotation picture, there would be no velocity at the center of mass because the object is rotating about the center of mass. So what happens when we take the motions and combine them for rolling motion? Well, let's consider for a moment how we would get rolling without slipping. Well, if you imagine something rolling without slipping and you think about the point that is in contact with the surface that it's rolling on, that point better be stationary compared to the surface. Otherwise, it would be slipping. And so the only way for that to happen, actually, is for these two vectors to be equal in magnitude to each other. And so the condition we need for rolling without slipping is for omega r to be equal to the center of mass. And if we assume that that is the case, so we're thinking about rolling without slipping now, then we can start thinking about what some of the other points on this object are doing when it's rolling. If you look at the center of the object, you can determine the velocity of the center of object by adding the vector that's at the center of the object showing translation above to the vector, or lack thereof, at the center of the object that's showing rotation. And so you'll get something that looks like this. Let's think about the top of this rolling object. Well, there's going to be a vector due to translation and the same vector in the same direction due to rotation. And so actually the top of that object is moving at double the speed of the center of the object. And you can keep going around. On the sides, you'll have vectors that are the one on the left-hand side is a sum of a vector that's pointed straight up and one that's pointed to the right, and the one on the other side is going to be the sum of a vector that's pointed straight down and one to the right, and so they'll look something like this. Okay, so where are we going with all this? Well, let me show you this picture. This is a picture of a bicycle wheel that is rolling. And you can see that the top of the wheel, the spokes on the top of the wheel are blurry, and meanwhile the spokes at the bottom of the wheel are not as blurry. and you can think about why that would be. And a good explanation is to say, all right, well, we know what the velocities are like here. For the wheel that's rolling along without slipping, the bottom of the wheel should be stationary compared to the thing that it's rolling on. And so, of course, if you take a picture, you should be able to see the spokes of the wheel in focus near the bottom of the wheel. Meanwhile, the center of the wheel is moving at the velocity of the center of the wheel, which is the velocity of the center of mass. And the top of the wheel will be moving at twice the velocity of the center of mass. And so that's the part of the wheel that's most likely to be blurry. If anything's going to be blurry, it's going to be the top. All right, so now that we have explored what this motion looks like a little bit, let's think about the kinetic energy of rolling. How would we calculate the kinetic energy of rolling? Well, just remember that kinetic energy involves translation, and you know how to find the kinetic energy of translation, 1/2 m times the velocity of the center of mass squared. And you also know how to find the kinetic energy of rotation. That's 1/2 I omega squared, where the rotational inertia there, I, is measured about the center of mass. Add those two things together, and you have the kinetic energy of rolling. And as I said earlier, there's no reason why the object needs to roll without slipping, but if you do set the condition that this is rolling without slipping, then you can also make the substitution that the center of mass, the velocity of the center of mass will be equal to omega r. So now we have what we need to start doing some example problems that involve rolling motion. And here's the first one that I'd like to show you. So here's a round object with mass m and radius r that's going to roll down a hill without slipping. And the question is, if the height change from the top of the hill to the bottom is h, find the linear speed of the ball at the bottom of the hill. Perhaps a better way of saying it is, if the height change of the ball from the top of the hill to the bottom is h, find the linear speed of the ball at the bottom of the hill. In any event, the first question we need to ask in these types of questions is, do we use energy or do we use forces or torques? We've seen already examples where we've used energy to answer a question, and we've also seen examples where we've used forces or torques. And most of the time, the way we make the decision is if it looks like the acceleration, angular or linear, is going to be constant, it's often useful to use forces or torques. And when acceleration isn't constant, typically we default to energy, and that's what we're going to do in this case as well. So as long as the rolling is happening without slipping, there won't be any loss of energy. And so we can just use kind of the classic conservation of mechanical energy equation. Kinetic energy at the beginning plus potential energy at the beginning is going to be equal to kinetic energy at the end plus potential energy at the end. Let's assume that when the ball gets to the bottom of the hill, that's going to be where the potential energy is equal to 0, or the height is equal to 0. So the kinetic energy at the beginning will be 0 because the ball, or the object, the round object, doesn't necessarily have to be a ball, is not moving at the beginning. And the initial height is h, so the potential energy at the beginning is mgh. At the end, we're going to say that the height is 0, so the final potential energy will be 0. And the kinetic energy that we're going to use is the one that I showed you on the last slide. We have to add the linear or translational kinetic energy and the rotational kinetic energy together to get the kinetic energy of rolling. So I'll put some other things in there to make it into an equation. And from here, you're really done. There's a substitution that you can make. If it's rolling without slipping, then we know that V is equal to omega r. So I made that substitution, and you can take it from there and solve for omega. The really interesting part of the problem is done, and from here it's really just algebra, so I'll leave it at that. and we'll move on to a new problem. So here's another one. A round object with mass m and radius r rolls without slipping on an incline. What is the linear acceleration of the object? So there you have it. It's rolling without slipping, so that's very nice. And the question is, do we want to use energy or forces and torques? Well, if you notice, the inclined plane is not curved at all. It's a straight line. And so, it's sort of calling out for us to use forces and torques, although actually it is possible to use energy for a problem like this. But if we're looking for an acceleration, you might guess probably forces and torques is going to be the way to go. So that's the way we'll approach it. And I will leave as an exercise to you to think about how you could use energy if you wanted to. So the first thing we're going to do is draw some forces here. So we know that gravity is acting on the object, and we can always resolve mg into its components, and the angle of the incline theta is going to be equal to the angle that I've drawn in there. We've also got a force of static friction. So if the round object is not slipping, then the friction is going to be static friction. By definition, you have static friction when something isn't slipping, so it's not kinetic friction. If the we're rolling with slipping, then you would have a force of kinetic friction there. There's also going to be a normal force, so I'll put that in. And when you have a situation like this with an object that is rolling, you want to have some equations that address translation and also some equations that address rotation, and typically you find some way to combine them in the end. So to begin with, let's just look at translation. So we know that the net force acting on the object should be equal to its mass times its acceleration. And to begin with, I would encourage you to consider just the x direction, and by the x direction I mean the direction along the incline. So I'm calling the x-axis the axis that runs parallel to the inclined plane. And so what are the forces there? Well, there's the force of static friction, and the part of mg that is parallel to the incline, and that's mg sine theta, and Fs is acting in the direction opposite the acceleration. So we get mg sine theta minus Fs is equal to mass times the acceleration in the x direction. Now, you're so conditioned to replacing a force of static friction with a coefficient of friction times the normal force that you might be tempted to make a substitution here and say, well, obviously Fs is equal to mu s times the normal force. But actually, the Fs is only equal to mu s times the normal force if Fs is the maximum force of static friction. And we don't know whether we have the maximum force of static friction here. We just know that some force of static friction is in play to keep the ball or the object from slipping, but we really don't know if it's the maximum force of static friction. So I'm going to leave it in this form, and instead of continuing on the translation side, I'm going to go over to the rotation side. So we also know that the net torque acting on this object should be equal to its rotational inertia times its angular acceleration. And at this point, we can apply this equation to, there are really two good choices for an axis of rotation. We can either choose the axis of rotation to be about the center of mass of this rolling object, or we can choose the axis of rotation to be about the point that is in contact with the inclined plane. I'm going to choose the first option. I'm going to think about the net torque about the center of mass of the object, and that's going to be the force of static friction times the radius. If you look at the other two forces here, mg and the normal force, they act right at the axis of rotation, and therefore they do not exert any torque on the object. So the only force here that's actually causing any rotation is the force of static friction. So that's my second equation, and from here it's just algebra. So I'll solve for the force of static friction. Now I can take this and make a quick substitution. We know that for rolling without slipping, that the velocity of the center of mass will be equal to omega r, but we can also say that the acceleration of the center of mass will be equal to alpha r. So I can replace alpha with a over r here, and this is what I get. And the thing that's convenient about that is then I can replace the force of static friction in the translation equation, do some algebra, and get this. The acceleration is mg sine theta over the quantity mr squared plus I com. And it's important to note that the rotational inertia that is showing up in this equation is the rotational inertia about the center of mass. If you look at the rotation side there, I was considering the torque about the center of mass, and so the I alpha in that equation was the rotational inertia about the center of mass, and so that's the one that shows up in this equation. So now you know a little bit more about rolling motion, and you've seen a couple of examples, and every time you see an example that involves rolling motion, I would encourage you to first think about whether you should approach the problem using energy methods or using F equals ma and torque equals I alpha methods. And once you get that squared away, you should be able to make some progress on just about any problem that involves rolling motion.